audience, David, Josh, Katerina, call you out by name. And I know Josh has to do your office hours at some point.
Yeah.
So yeah, this is very, very
cozy.
Yeah.
We should sit next to each other.
I know, we should all group. Okay, so Hans, I invited him to give a talk on a problem that we're seeing a lot in manufacturing these days, which is how do you take really complex modeling and then apply it in real time so that they can get feedback on like the factory floors, wherever they're working on. And these are really complex multi-physics simulations that they're working with. Hans, of course, started in a very different area, but now applying it here in manufacturing, and so it's a very neat project. Take it away, Hans.
Thank you.
Can I stop you to begin with?
Yeah,
Sure.
You already have a question?
Well, what is multi-scale and multi-physics? If you're covering that in your talk, then I'm good, but if it's someone that everyone knows about me, then I'd like to...
I will talk a little bit about that and give you some different examples.
Okay, thanks.
And it's helpful because, and anyone, I guess, online, however one would interrupt online.
They tweet in.
Okay, great. So you're watching the tweet,
watching the tweets.
the Twitter feed. So I'll try to keep it general, and please do interject and ask those questions. Peter, I originally thought this was a 20-minute talk, and so I'm covering more than just the manufacturing. I'm actually going through a bunch of different things.
The other models, yeah.
Very good. All right, so I'm Hans Johansen. I'm in the Applied Numerical Algorithms group, and if you've heard other talks from Lawrence Berkeley, you realize we work in very large distributed teams, often all over the country and the world. So I have a laundry list of people that have helped me with various pictures of things you're going to see today. So the challenge of accurate, fast, multi-scale, multi-physics simulations, a lot of things there, but multi-scale in this case means you might have things at 1,000 times or even 1,000,000 times different physical scales in space or time. And multi-physics in this case means you don't just care about one thing like heat transfer. You might care about heat transfer and chemistry, fluid flow, heat transfer, and chemistry. Radiation, heat transfer, fluid flow, and chemistry, right? And that list, you know, if you think of the physical world around us, that list is as long as you want to make it. And the whole point of making science possible is to be able to make the simplifying assumptions that get you to a point where something is just feasible to be both novel and possible to compute. So that's pretty much what this talk is about. And that's a moving target. Somebody could be brilliant with mathematics and all of a sudden something is computable. Somebody could be brilliant with modeling and all of a sudden something is simplified enough where it's computable. Computers can get 10 times faster in 10 years, which we have seen for sure, if not more. And now all of a sudden something that wasn't computable before in any reasonable amount of time can be. So those are the trade-offs that I'm going to talk about today. I'm also a little bit of a contrarian, I'm warning you. So I'm going to show you kind of classically what you might call a pretty movie. A lot of science talks start with things like this. This is actually a shallow water equations, which is basically modeling the Earth's surface as if it were a single layer that was all moving in unison. You can use this, for example, for vorticity dynamics in the ocean. It's a simplified model for the atmosphere. This is a particular simulation which is showing adaptive mesh refinement. These patches here are where computational resources are being concentrated. I'll play it one more time. The reason I threw this up front with no context or history or anything else is a lot of science talks start with pretty pictures or computational simulations that are these dynamic movies, and you have no idea if they're right. You know, if you're an educated person in this field, you can say, all right, well, that looks like a lot of things moving around and maybe complex dynamics, and I see some interesting features here and there. So part of my point with the talk today is that I think when people start doing multi-physics, they gloss over all of the background and thought that goes into simplifying things to the point where you can actually compute them. This is a completely inappropriate model for the ocean, unless you're looking at something very specific like a tsunami wave propagating across the Pacific Ocean. So I'll talk a little bit about that model, for example. But it also highlights how you can create these discretizations where, for example, each of those cells there would maybe be 50 to 100 kilometers on a global scale. That's pretty coarse. These finer ones are down at 5 kilometers resolution, which is about the limit of computational throughput for ocean simulations today on a global scale. So this is just in a nutshell an example of how you can go across those different scales, factors of 10, factors of 100 in magnitude, simplified physics, simplified environment, and pretty movies. But is it right or not is the question. So what challenges do we see in multi-scale physics, for example? So we have these computational science goals of trying to provide a high fidelity or good answer. And so asking the question, are we solving the right mathematical problems on the computer, is a really important starting point. And then you also have to ask yourself again, all right, so I have a mathematical model and I'm applying it to a specific problem like a tsunami. Am I doing a good job, or have I oversimplified things, or are there things I just really don't know about? For example, what does the bottom of the ocean look like? If you'd asked that 100 years ago, people really had no clue. Today we know we do, and we can get ever higher resolution of it, but that resolution costs computer time and other things. That's great, Zushin. Thanks for coming. I actually included one of your results in here. The second question for these multi-scale physics trade-offs is accuracy. So if we've got a representative mathematical problem, are we doing a good job of actually solving that mathematical problem in a way that is both feasible and that we have confidence in our numerics, for example? And are we certain that the data and the parameters we're using, are those valid enough that we can actually say, yes, this result is now a valid multi-physics simulation, correctly computed to compare to the real world? So fidelity, accuracy, and the last one is efficiency. If all those things are perfect and we still can't get an answer out in 3 weeks, then maybe that's not a real-time system you want to work with. So for example, if we were to take a model and do tsunami warnings, right? You have to be able to turn it around within hours to make sure that you understand the impact of something across the Pacific Ocean, for example, or to understand where you might provide warnings or evacuate people or things like that. And we're still not at that point with weather. We're still not at that point with things like natural disasters. And we're just getting to that point, I think, with manufacturing problems that are much more within our control. And so I have an example of one of those. But the other thing we have going for us is that we have computers that are just growing so rapidly. It's crazy. So one of the things that our group does is to try to take advantage of every bit of computing power we're given by these big investments in supercomputing facilities like NERSC up here at LBL. Technologies like many core processors, vectorization, GPUs, things like that, they're all trends that have basically given us 100-fold in computing power just in the past 10 years. And then the last question on that, so we got one simulation done in a reasonable amount of time. Do we have enough simulations to build up our confidence levels? And one of the things that we see a lot is hero calculations, where you just push through the calculation, you got it done. I simulated an earthquake, great. What does that mean in terms of earthquakes in general? Did you do enough statistical evaluation of the weather to be able to say something about climate instead of just a single weather event? Things like that. So I see our computational science challenges for these kinds of problems as this just continual trade-off between solving the right problem, solving it correctly, and solving it fast enough that the answers are useful and at a resolution and accuracy that we care about. So the rest of the talk basically fills in those gaps. So here's an example of some work I've done with colleagues up in the basically the environmental sciences division. And up here, for example, this is a classically high resolution simulation of climate on Earth. That's what it looks like in terms of the mesh that you'd use to discretize things. And you can start adding higher resolution things over California if you want to start, for example, picking up mountains, watersheds, even just the coastline. At resolutions like this, San Francisco doesn't exist, the Bay doesn't exist, you don't see it, right? The coastal range doesn't exist. The Sierras are a small blip that goes about 1,000 meters up. So when you do these really coarse simulations, you get the fidelity of a global simulation, accuracy-wise, but you're missing out on the things you may really care about, like how much of this rain is going to end up being water for us in the summer or next year. So some techniques you can use, this is a different kind of adaptive mesh refinement that's just static, but it's adapting around the things you care about. In this case, watersheds, the peaks of the Sierras. And the difference between a 55-kilometer resolution and a 7-kilometer resolution in terms of the errors, that's the red and blue in these plots, is huge. Basically, the topography doesn't exist at the computable resolution. So you have to be smart mathematically and algorithmically and physically to get it to the point where you can do something that is actually more accurate for what your interest is in the scientific questions. So that's an example. And one of the reasons that this historically has been a problem is that it wasn't computable to do these high resolution simulations. So you were just hoping for good gross statistics and trends. Mountains, for example, are represented by these jiggity-jaggedy terrain following meshes, for example. And you can show by looking at the statistics from those previous meshes that, for example, 1,500 meters in error between a 55-kilometer simulation and a 7-kilometer simulation. You know, this binning of errors, basically the only thing, you can barely see the green here in this, but 7 kilometers is closest to reality. It's still not great, but you're completely missing the peaks of the mountains, and it's changing with every simulation. So if you had a series of these simulations and you're trying to draw statistics from 3 or 4 of them in the series, you've got no hope when you've got this shape messing with your mesh, messing with your solutions. It's computable, which is nice, and it's fast, but it doesn't give you the accuracy that you want. So that's just one example from climate and weather. And I was really disappointed to miss the NOAA talk yesterday. I hope that was kind of in the same vein about computing power.
It's archived and you can watch it online.
I will do that. So here's another example. So this compares whether we're solving the right physics or not. MG1 is named after Morrison and Gettleman, who were some physicists that started talking about, all right, if we have to model rain and clouds at a global scale, what is cheap enough for us to calculate on yesterday's computers? And so they came up with this algorithm, basically says if it's going to rain, it dumps, it lands on the ground directly underneath that cell, and that's good enough. At least then we have rain coming out of the atmosphere and we have evaporation going back up over the oceans. More recently, although it's still not in many global models, they've done a second version of this where they're like, you know what, rain doesn't instantly puddle on the ground. You have to let it drift. It can move horizontally with the wind. So we have to be much more careful about its interaction with elevation and mountains and other atmospheric phenomena. So here again is this really coarse simulation at 55 kilometers, and the statistics are completely wonky. If you look at the peak here from observational data, we're missing all of that. And that's primarily because the rain is puddling and there are no mountains, right? So even though you improve the physics model, you're at a resolution where it doesn't really make any difference. It's not going to help. You have systematic errors in your work. This was with my colleagues Zhixin Zhu and Alan Rhodes. Just a simple doubling of the resolution, which means 8 times the computational cost for this model, gets much better statistics. And you can see now we actually start to have things in the 2,500 to 3,500 meter elevation. We actually have mountains again with a simple 8 times improvement in computational cost. This one is another factor of 8 cost. But because we're being smart about where we refine over California, the statistics are improving for the things we care about, and the global cost, if we were to do that simulation globally, it would be weeks on a supercomputer, and it's just not feasible anymore. But because we're doing it regionally just over California, we get better and better statistics. And so finally, we're starting to see a separation between the old way of doing things down here, which doesn't match these statistics very well at all, and the new way where the rain and the snow actually end up where they belong. And now we can start talking about water resources. Yes?
Are there corresponding observations for the temporal domain?
For the temporal domain, these are seasonal averages, basically. Right, so because in California, we get all of our rain and snow in a 3 to 4 month period, basically.
In terms of meshing?
One more time?
In terms of meshing or steps?
No, this is just static. This is just trying to get mountains. Yep. And especially one of the things we're interested in is which side of the mountain does it fall on, because it matters whether Nevada gets the water or we do, right? So getting those watersheds resolved and getting the altitude of those watersheds so we know if it falls as water or snow is a very important thing. So this is an example where we finally, after, let's say, what's this in, maybe 25 years from MG1 to MG2? 15 years. We're solving the right problem, and we just have the computational problem to solve it at the right resolution, and then we're finally starting to get the right answers. So that's quite an accomplishment for the field, but I would have hated to have been in the audience feeling confident about my answers 15 years ago. It just wasn't feasible. This is work from my colleague's paper using a regional forecasting model called WRF, driven by real data, which is basically reanalyzed satellite data called NCEP, versus that same variable resolution model, which I will call untethered. It's simulating year after year after year without any data input into what's actually happening. It's just being driven by the previous global climate model. And look at the uncertainty here. This data is actually from satellite, and even though we're using that to drive the model, it's getting something not too far off from the observational model, although this is satellite, so you're not entirely sure, but it's in the right ballpark range. And if you look at the variation of this free running or this non-data driven solution, look at the huge variation across these resolutions. And I can't say there's a trend to converge from 28 to 14 to 17 or from 14 to 17 maybe. So I still think this is the kind of open question of, we might be doing physics simulations correctly, but are we incorporating data in the best way possible? And then can we draw long-term statistics from those kinds of simulations that are free running? So I think this is still a very open area of discussion. We might be able to get weather right for the next week, but I still feel that for the long term, we're having a very hard time getting climate. And one of the things you can see is that what we're doing is adding resolution, solving the best physics problems we can, but we're still missing something about the climate statistics that's undermining our ability to do all the mathematics correctly. So here's a potential solution. We saw that jagged terrain following mapping. Maybe we keep things smooth. Maybe we map it in a way that our numerical answers are better. But we do some representation of the real actual topography of the mountains. And now this might be able to get us certain properties, like that's just a mathematical expression for conservation in mapped grids, so that you make sure that rain, the clouds, things going in and out, you get those. So here's an idea that I'm pursuing where this stays the way it is, and the mesh is actually a thing that coarsens. And there have been some other authors who've had some good luck with this for tsunami modeling. This is somebody at NOAA named Alistair Adcroft there. And he's the head of the ocean model development. And he's done some great work where you do these super high resolution tsunami modeling. So you probably don't recognize it, but that's Sri Lanka, that's South India. So this is the Andaman, 2004 tsunami from the earthquake in Indonesia. And you can see these are the gross things in terms of magnitude and the waves that are going to be pounding Sri Lanka. And this is an incredibly coarse resolution. I think this is 64 times coarse, which means it is 1,000 times cheaper to compute. But he's getting the peaks. He's getting the wavelengths to some extent. This is garbage probably and noise, but maybe it's enough to indicate, well, at least that region needs to be under tsunami warnings, right? So here's an example of how, I'm sorry, there it is. So 2 feet by 30 feet, roughly 16 times, so 16 cubed is still 1,000. So basically, he's come up with an approach where he can modify the way the bathymetry of the ocean and the coastline are represented and still get decent answers out. And this is the kind of thing you'd need for a real-time system response, right? If you're going to do tsunami warnings, you have to do something that's simple enough to run multiple scenarios in a very tight time frame. So the way he did this was to basically, instead of this, which is the typical ocean modeling approach, or this one, which is a kind of slanted, slightly better approximation of what could be a very jagged ocean bottom, he basically asked the question, well, the point of the ocean bottom is to inhibit flow and damp flow. And so he came up with a very simple model for what the bottom of the ocean would look like if it were represented coarsely. And that's how he got such great results. So that's an example of what I would say a reduced order model that makes the problem computable, that retains the best aspects of a high resolution model. And he's done this all without adaptive mesh refinement. If you added something like adaptive mesh refinement to this just for the front waves, then you could get more computational gains from it as well. It's also, I think, a great opportunity for satellite observations and machine learning to start deducing reduced order models for us. What is the nature of the model we should be solving in order to do a better job at coarse resolutions? Because I can brute force the fine resolution job all day and spend weeks and months running simulations at NERSC. But I would hope to then take that data and maximize its value in terms of educating ourselves around what's a coarse solution that's worth doing. So that was one example. So let me circle back. Fidelity. Are we solving the right problems? Do we have mathematically reasonable representations? If we're careful about them, and if we put some thought into them and really challenge the assumptions. And then the question, have we oversimplified things or relied on uncertain assumptions? We absolutely do that routinely. And that's where I think the field needs to have a lot of intellectual honesty in order to make sure that we're doing a good job with that. So on to question of accuracy. So here's an example of something we do in our group, which are called cut cells, where you have something like that really complex terrain. In this case, it's a very smooth interface, and you run it across your relatively coarse mesh. The nice thing about this is that's the San Francisco Bay Area bathymetry, for example. You can do some very good jobs with rugged coastlines. I can get this down to whatever resolution I want, and I can still put it in this form where I'm guaranteed that water flowing into the bay ends up flowing out of the bay. Conservation is what we call that. So these kinds of natural conservation laws are things that come out of physics, and you want your reduced order models and you want your simulations to respect those kinds of aspects of things. The other nice thing about this is if you're trying to do that adaptive mesh refinement technique, you can reduce the domain of dependence of your mesh to just locally what you're refining. If any of you have worked with finite element codes before, they're really good. One of the biggest hassles, if you wanted to mesh complex things, I'll just skip forward to the picture here for a second, I'll come back to this. If you wanted to mesh complex things like this, like for example, that's a nuclear core reactor with spinners and mixers. That's the old San Francisco skyline before the Salesforce Tower. Corals, the bay, other complex geometries. This is a X-ray tomography scan of crushed calcite that one of my colleagues in our group has done. And he's doing full 3D reactive simulations, multi-physics, multi-scale, on these domains in order to try to get an understanding of how reactions happen inside of subsurface carbon storage questions. So just to kind of go back to what you want out of these kinds of schemes, conservation's got to represent physics accuracy. That was the point that I was trying to make, which is that if you calculate a solution and it look great, my solver converged, or it looks about right, or whatever those kinds of thumb in the air eyeball norms are, that's one thing, but it's worth putting in the extra effort so you're not deceived. And I'll give you an example of how the deception can happen. Consistency, so free stream preservation, accurate fluxes, these are all concepts. I know we've got a very diverse audience here, but basically you want it to have similar physical characteristics to the system you're modeling. When water flows, if nothing gets in its way, it more or less flows in a straight line, or it's stable if it's under a certain Reynolds number, those kinds of questions. Stability, this is just a question for meshing and how we deal with small cells. I won't get into that. Simplification. So the last point I made on efficiency for these kinds of algorithms is you want it to be as regularly structured because computers like regularly structured calculations. They're best at those. Our newest supercomputer, Core Phase 2, has 9,000 processors, each of which expects its cores, 68 of those per chip, to get precisely 8 doubles that it can chew through like an assembly line to do a calculation. If we start breaking that up with unstructured calculations and looking down neighbor lists and things like that from a computing standpoint, we've wasted probably 50% or more of the cycles of this supercomputer. So we design our algorithms to not only do the right thing in terms of accuracy and mathematics, but to make sure that we get low memory vectorizable discretizations in most of our computation. I won't go into the rest of those. So here are some examples of how people do these kinds of complex geometry cut cell approaches. One of my collaborators at Duke has done something called extended finite element methods, where you have a typical unstructured finite element mesh, but you do these intersections. There's some work done for very complex thin body domains. Other ones where you have these domains of dependencies and something called immersed boundary methods, where you're approximating the forces based on how those interfaces interact. Some colleagues down in UC Santa Barbara do complex multi-physics problems like Stefan problems, where you have a phase change in a moving boundary. And one of the real questions is, if you have a phase change, you want to conserve the energy liberated in the latent heat from those kinds of things. So these kinds of problems are very interesting for material properties and for asking questions about crystal growth and those kinds of things. Again, manufacturing-wise, these are really important questions about how do you do moving boundaries accurately, but yet cheaply enough that you can modify a process as it's evolving, like if you're doing chemical vapor deposition or things like that. So here's an example of one of my colleagues who's doing great work in using a discontinuous Galerkin method. The reason I'm putting this up there is that you can see that the error that he's getting looks very erratic. But if that's off in the 6th or 7th or 8th digit, that's okay. That's a good solution, right? This colleague here, a former postdoc of ours who's now at NASA and doing some good work there too, I can't tell if that's a good answer or not. This is for aeroacoustics around landing gear on a body. Now, granted, you could look at frequency content, you could look at what's the energy spectra of this turbulent flow and things like that. This is a smooth problem. This is not a smooth problem, right? So asking the question around how accuracy and stability of the numerics and the computations of these things interplay is really an important question. Some people will do work just to try to kind of limit their algorithm to the places where it's stable. Others will push it to the boundary and say it's unstable, but it's getting into the right accuracy range. So those are some questions there. I think I'll skip this, but basically these cut cells, there are lots of ways of going after the small cell problem, which leads to stability issues. We've come up with a novel way of doing it, which is a little bit more mathematical, but this gives you a sense of how complex some of these boundaries can get when you're dealing with things like moving crystal interfaces or those complex terrain following, or getting rid of those complex terrain following meshes. One of the things that's interesting about accuracy in this case is the question, if you have a really smooth problem and a really smooth solution, do you trust the answer for this? Well, we can get 10 digits of accuracy on a laptop with this kind of a simple problem with certain boundary conditions. There's a kid outside playing basketball, so it's kind of... the second... Thanks, Peter. I'd go out and play with him if I didn't have to talk for the next half hour. So in this case, though, this is just another very simple geometry, but the geometry is kinked in these corners. In fact, if you look at it, mathematically, it's a well-posed problem, and I could apply a 12th order accurate method to this. But if you do the analysis on this, the mathematics doesn't like the kink. The interface there, although it's well posed, as soon as you discretize it, you're introducing discretization errors, and then your solver is solving a modified problem, which is not correct anymore. So basically, I went from 10 digits of accuracy in my solution down to 2 if I'm lucky. And if I beat this to death with computational power, it's not going to improve very much beyond that. So I know this is a huge chart of numbers, but this just shows you how you get 2 digits here, and you're working really hard. In 3 dimensions, that would have been 10 to the 9th degrees of freedom, but it's a huge resolution improvement with an old algorithm that we've used, and it's not even converging, right? Now, our current algorithm that we're using is much more higher accuracy, and it's still not converging too. So you see this kind of problem, you get a pretty picture, and you see 2 digits of accuracy, and you say, okay, I'm done, right? That's as good as I can get. Well, it's not true, because from an accuracy standpoint, if you look at it mathematically, you can do all of these modifications where you can say kinks in the geometry should be smoothed out to some relative level of accuracy as my computational solver. There are mathematically clever ways of doing that with mollifiers and smoothing functions. And when you do that, not only did I improve the old method, where I'm getting 5 digits with a billion points, but my really good method gets to that point at extremely coarse resolutions, right? So look at that error versus that error at basically 30 squared times, so 1,000 times the resolution, 1,000 times number of points, fewer. So my point in putting this out here is that clever mathematics doesn't get you very far unless you actually understand the problems, apply it to the right kind of problem, chase it down, work with it. And this algorithm here is extremely fast on supercomputers because it's organized in a way where you use the processor as much as possible before communicating memory or bytes or other things. So here's another example of accuracy winning out in the end. Here's another one kind of mathematical theory-wise. If you don't do the right thing for the stability of the algorithm, you end up with this really noisy representation of the differential operator. This is supposed to be a very smooth Laplacian, which is what's over here. You have to do a very specific way of looking at the least squares system in order to get this smooth behavior which more closely mimics the physical system, as opposed to something which, if you just look down here in this coarse range, is about the same or correct, but as soon as you try to apply it at scale, all your frequency content is just garbage. There's another example of this. This would be for pure advection. These are classic algorithms that people use that have decent accuracy. That's second order accuracy, that's fourth order accuracy. This is a representation of the Fourier symbols of this, and this has a 2 delta x mode. So basically you can introduce plus minus noise. Then people start fixing those up with filters. They start adding extra resolution and filters. They coarsen things. There are all kinds of tricks that people play. Well, if you're good with the mathematics, you can get rid of that 2 delta x mode and smooth it out and even kill it. And if you're really good with your mathematics and put in some computational work, you can get something that's behaving almost like the mathematics would say it would in a pure kind of Fourier sense. So, kind of back to this question of accuracy. We've picked a mathematical problem. We've tried not to oversimplify it for our physics problem. Now we're asking ourselves, did I solve that problem well? And again, if you're careful and realistic and you really scrutinize and don't just take things at face value, you can do a good job with that. And it takes a lot of testing to build up that level of confidence just in these simple mathematical problems. When you get to multi-physics problems, now you have to tease apart every little bit. And there are much more complicated interactions and coupling. So this last question of efficiency, I'm going to highlight one particular software technology. There are other things going on. Are there any questions on Twitter space?
A question, just generically, I was going to save it a little towards the end, was what about running a series of simulations, say, the tsunami or whatever, your weather over the state of California, and then using machine learning to help you interpolate between different, you could imagine earthquakes occurring at different locations, and then using machine learning to interpolate between to, quickly say, oh, here's what it would happen if it was a magnitude 7 at this location rather than the 2 8s that I ran.
So basically, limited number of simulations and using machine learning to fill in the space in between them.
Yeah.
So high dimensional interpolation is what that gets called sometimes, I think. And I think it depends very much on whether you can expect the problem to be continuous. Well, let's go with the earthquake example. If I started off with a problem that was coarse and I'm moving to one that is finer, then there was information that the machine learning algorithm will never see, right? So the interpolation might not even be in a valid range because it's just starting with bad information. It's like trying to train something that's recognizing images of people starting with images of plants, right? You might get lucky, but most of the time it's not going to happen. I think the use of machine learning for that kind of filling in the simulation experiment is much better when you have these expensive brute force but correct models. And maybe that's what you're seeing in astrophysics and cosmology, which is that all the models are high resolution and correct, but there's so much data it's impossible to try to analyze it in all those dimensions, and machine learning's chewing through that. So that would be my guess. I've also seen good work where people will say, my brute force simulations, I know solve the right problem. They solve the problem I've given correctly, but it's not matching observations. Use machine learning to find where that gap is, most likely, right? So what was the assumption I made that doesn't fit the observation as well as I would like?
And then one other question was the underlying multi-physics models that you have. There's some uncertainty in how you parameterize things. How do you flesh that out through a simulation?
Yeah, so if you pick constant parameters, for example, and you have analytic solutions, you're happy, right? You know you can match those, and when you get a good answer and it's numerically convergent, things work well. when you have uncertain parameters, in fact, the chemistry example I'm going to bring up next, or those cloud examples, you can try to bracket it and do a bunch of simulations in those ranges. You can try to run ensembles and ask if the ensembles match, like the work that we were doing with the California snowpack and rainfall. But that's kind of open question, right? Okay. And you wanted me to stop at 20 after, right?
Yeah.
Okay, all right. Okay, so now I want to get into efficiency. So, we can throw all the physics in the world and all the resolution of the problem and take the smallest possible time steps at the level of atomic interactions, and it will never finish. So what's the point? So we have to figure out that sweet spot between what's computable and what's actually scientifically interesting and or reasonable. And then finally, we can't just do these hero runs. Did we actually get enough statistics in our ensemble to actually have confidence in our solution now? So I wanted to show a little bit of how the geometric variation in these things, like here's an interface that's being represented in some work by my colleague Robert Say, who's doing great stuff right now, where he's going to have to do all the geometric variations of these surfaces in order to do an ensemble big enough for all of his work. But notice how in most of the domain he's expressed something that looks like an efficient grid data structure, and he's just making exceptions to that structure near the boundary. So even if he does move this a couple of cells, maybe every couple of time steps in order to evolve the interface and do the right physics, he's still, for the most part, got a regular structure in his calculation. There are other examples of this that they're not really worth going into, but basically people will bend over backwards to do a one-dimension lower, more expensive calculation and retain a higher dimensional regular calculation that they know they can optimize like crazy. That means by the time you get up to 1,000 processors, maybe only 100 are responsible for these irregular calculations. Maybe you can distribute that 100 processors worth of work across 200 processors, and it goes twice as fast if you're lucky, depending on how you design things. So even though multi-physics and multi-scale has a lot of irregularity in it, and I'll show you physics irregularity in a second, you can do things to try to modify that. Here's another example for hyperbolic problems where this is again my colleague David Trebedich at LBNL, where he's got this cylinder packed. It's meant to be a reactive cylinder where he's got it packed with spheres and he's pushing gas through it. And he's asking about the reaction dynamics on the surfaces of those spheres. And one of the things about the mixing of the gases and the temperature and other thing that's going on here is this is kind of happening everywhere, but if he only cares about the reaction, he can focus on this area here. If he only cares about the final pressure, maybe he doesn't add any resolution here. In general, he's going to focus on the things where the physics are most interesting in determining the final state of the system or the quantity of interest you're looking at. So even though this is a fairly complex gas flow plus diffusion of heat and species, plus the chemical reactions going on there, running on 100,000 cores, it's still going to have all these different aspects. He's going to have to focus the effort in specific parts of the domain where those things are happening. Here's another example of shock dynamics. You can't see it very well here, but these boxes are the adaptive mesh refinement of a shock hitting a sphere and then just capturing the areas where the fluid flow is not kind of constant or background. So you can see this entire wedge here of adaptive mesh refinement around the boundary of the reflected shock off of the sphere, and also trying to capture the dynamics on the surface of the sphere, which could involve things like a boundary layer or viscosity or heating or things like that. We've applied this adaptive mesh technology in our group to a couple of different problems. For moving boundaries, I've done this work where if you wanted to do, for example, wave energy conversion, and you wanted to look at free ocean surfaces and what the pressure fields are and how could you tap into those pressure fields to try to drive a energy converter that could take that wave motion and turn it into electricity. Well, in order to do that, you need highly accurate solutions at the surface that propagate smoothly down in the interior, and then that turns into a real-time control algorithm for this multi-physics system. So I've got the ocean dynamics physics, right? What is the spectrum of waves? How often do we know that we get different kinds of waves? We have the control algorithm for the wave carpet, which isn't in this. So when I see different kinds of waves coming, how am I going to modify my system without having to do these simulations in advance to have a reduced model to be able to control these kinds of algorithms correctly? And then last, what maximizes or optimizes the power takeoff for these kinds of calculations? Up here is a colleague of mine, Dan Martin, who's doing modeling of the Antarctic ice sheets. And that little region there has 4 or 5 layers of adaptive mesh refinement to try to capture where that ice sheet hits what's called a grounding line. It's the last spot where it's supported by the land, which could be under the water, right? So you can try to figure out how rapidly the ice sheet is going to move based on these incredibly long time spans of, hundreds of years, basically. So in this case, it might not be a real-time control loop, but when you think about it, we're driving this ice sheet model with all these sensitivities on the atmospheric temperature. How much is it going to snow in Antarctica? What's the average temperature over periods of the next 20, 30, 100 years? We're going to have to run gazillions of simulation scenarios in order to try to figure out what percentage of those scenarios will actually accelerate the ice sheet flow and then cause sea level rise, for example, right? Or is there any sea level rise at all due to this or not? So those are questions where the efficiency of this calculation is really, really important. You cannot use a uniform mesh on Antarctica and expect to get it done in your lifetime. So he's done this adaptive mesh refinement just for these particular glaciers and can attack them one at a time in a very adaptive way that uses the computers efficiently to do it. And lastly, GCM here is global climate models. Now, this is some work that I'm still wrapping up on what you would do if you wanted to take that shallow water vortex model and make it much, much higher resolution and actually be able to track, for example, tropical cyclones at high resolutions that we can't do today, like a kilometer, but making sure to capture the global context of flows and things like that. One of the problems that we have with tropical cyclones and other kinds of dynamics is that what's computable at a global scale is absolutely infeasible in terms of its scientific value. You might get some statistics out of it, but they're mostly short term. And in fact, tracking hurricane paths is still a very open challenge. I don't know if the NOAA folks talked about that at all.
Tornadoes and
Yeah,
severe storms.
but that's a huge multi-physics problem where you have surface temperatures, you have the previous tropical cyclone stirring up the ocean and changing the amount of available energy for the next tropical cyclone that might pass over in a few days. These are complex, multi-scale, multi-physics problems, and they require really good numerical algorithms. And again, this question of feasibility and what you can compute and what you can't. So we have other examples of shock dynamics, and this is an advection diffusion test problem and things like that, where reactions in this domain allow you to concentrate just the extra computational effort on these small regions where it matters the most. Like, would I calculate cloud cover and things like that on the rest of the globe when I'm simulating a tropical cyclone? Probably not. I can calculate only where things are the steepest gradients or the highest values or the most important for my scientific goals, and leave the rest of the simulation at relatively coarse resolutions and work on that. So again, the efficiency of these algorithms comes from some software investments that we've been making over the past 10 to 20 years, some smart collaborations with scientists to know where we concentrate on the physics and what physics needs to be included to get a decent answer, and then on the numerics to make sure that we get the most out of every aspect of the computational systems that's possible. So this is just a simple example from this manufacturing project we have. This cool thing called a clip process, where they illuminate with ultraviolet light into this resin, liquid resin, and they draw out this solid part, which can be as complicated as a mesh. They're actually making dentures now too, down to I think a 100 micron resolution. And the problem is that they can only print these things as fast as their current models allow, and it's a real-time system, right? Every part is going to have a template, and that template is going to be projected and created on the fly. So we've helped them come up with a chemistry model that's a reduced order model to some extent. The spans from this 10 micrometer layer where the reactions are happening, the fluid flow, this is just a model fluid flow, and then the final part shape, so that they can improve their tolerances, they can do a better job with their reactions, and the ultimate goal is to hope to be able to do that in a real-time basis, where we've given them a reduced order model that they can use to adapt to how the parts are being printed. If they want to draw it fast and are willing to accept a lower tolerance, use this part of the algorithm. If they want to be extremely precise and make sure that they don't get any tolerances outside of their design goals, then you do a different approach. So this is basically how we start building it up, though. This is a reaction model, for example, if you had the ultraviolet light just in this region, and it's consuming oxygen, and it's got this conversion where it's the polymers going from basically a inhibited monomer into one that's actually going to solidify into the part, and it starts behaving like a solid part. And if you look at the numerics for this, basically all this part, we don't need to do any reaction calculations out here. So immediately, if you just ballpark it in 3D from an eyeball norm, we could save a factor of 10 in our computation efficiency by just recognizing the physics is only happening in certain regions and then building that smarts into our modeling. Another thing is the rate of change of this. This shoots up initially and then it slows down, shoots up then slows down. So those gives us opportunity to change kind of the dynamics of the timing of things. And then this is the last one, which is a little tricky, which is that this is a mesh imprinting. So basically, as you're doing a calculation like this, where you have a reaction that happens every time you kick over some concentration value, you'll get these spurts, which are very unphysical in terms of how these reactions progress, when really what you want is something that's kind of smoothed out and more accurate, even at coarse resolutions. So one of the things we're working on here is a reduced order model that will make sure that any of our numerics that are under-resolved, kind of like that tsunami simulation, still get us a good answer. And that's work in progress as well. But it's really important for these guys because all of their complexity comes from the fluid flow, which they can't really observe, and what they know about the chemical reaction, which they're very confident about in a static kind of chemistry laboratory environment, but they're much more concerned about when it comes to the dynamics of things. So this is just one more example, but I'm out of time. Basically, you can be smart about how you represent geometries, and then you can do some very complex multi-phase physics, multi-material physics as a result of that. So let's kind of wrap up. So the challenges for these multi-scale physics problems. We can do a good job with the science, with good collaborations, and with good mathematics representing the problem as best we can, but a lot of times we still introduce a lot of uncertainty. Can we solve the mathematical problem correctly? Most of the time, yes. I think every person with good numerical training understands when to be careful about that. I think people that use packages have a much harder time of knowing whether they're getting a good answer or not. And the way you get past that is with a lot of extensive testing to make sure that you can trust the answers coming out. It's not just looks right. A lot of investments in clever numerics and computationals and computer resources like NERSC and scaling up the software for them for things like adaptive mesh refinement and computer science advances and things like vectorization and many-core and threading. We can get the calculations done in a reasonable time. But I think we can never actually get enough simulations. I think you've talked to any scientist, they just wish they could run the whole computer all the time and it would be theirs, especially the quantum chromodynamics people. But I think the lesson learned here is that we get better and better with these things every 10 years, and the opportunities become more and more real in terms of what we can actually design. And I think we're getting more and more close to kind of a real-time view of modeling reality, which is really exciting. So thank you for all your time.
One other question here, which was on the clip modeling that you showed. What feedback do you get from them observationally to help, understand that you're doing the right thing? And so how do you compare a result that they produce with your models? What goes into that?
As much as possible, right? For anyone that's done computational models, you want to get as much data as you can. This is an example of particle image velocimetry. There's a movie that goes along with this where you can see each of those shiny particles getting drawn up and into the resin. So we can get a velocity field for a particular part shape. So that's an example of something we could validate against. This test is actually something they've done routinely to try to measure how fast their chemical reactions happen. And so this is what they call a dot test for this company. And they actually know if you draw a slice across, in fact, that blue line was the data we sent to them. Along that line, you can see how the rate at which that reaction happens versus time. Another great example. But of course, the ultimate proof is they have a printed part, we predict a printed part, and you look at the two of them and you say, well, that looks more like a plant than a person. So,
Okay.
right.
So it's still kai by eye in some sense.
Absolutely.
Okay.
Yep. But building it up from confidence from little parts is a good way to at least build your confidence in an end simulation.
Any other questions? Yeah.
So going back to one of your requirements, conservation requirements.
Yes.
Is that, say in practice, is that conservation at each delta t, or conservation eventually,
It always depends, right? Just to repeat the question for those that couldn't hear it, asking about how stringent are the conservation requirements. If you're doing shock dynamics, you don't get shock speeds correct if you do not have strict conservation every time step, every cell. That's just kind of the mathematical nature of things. If you're doing chemistry, conservation is extremely important because it helps you eliminate unphysical behaviors like negative concentrations of oxygen or reactions that don't stop when they're limited by the amount of components that you can put in. So conservation, we're very strict about it in general. For things like, for that clip process, for the printing process, do you care about momentum necessarily as a conserved quantity? Probably not. It's such a viscous, gooey thing that it disappears. Kinetic energy, probably don't care about it. But thermal energy, because it affects the reactions, you better conserve some kind of thermal/chemical reaction energy. Right. So it absolutely depends on the problem. And my training's not just numerics, but it's also mechanical engineering, and I've had exposure to lots of computer science techniques. I think the best people in these fields are ones that can bring together all those different disciplines humbly and ask whether they're doing a good job or not.
Any other questions? Let's thank Hans again.
Thank you.